Okay, ladies and gentlemen, let's continue with chapter 9 on natural convection. Today we're going to do combined natural and forced convection, and we make use of the textbook of Cengel and Ghajar. Paragraph 9.6, combined natural convection and forced convection. So, as a general statement, if we think of convection, then up to now we have done external convection, we've done internal convection, but all of them were forced convection, and we've covered those in chapters 6 to 8. Chapter 6 was the fundamentals of convection. Natural convection is now here in chapter 9. So if we think of the fact that for all practical situations, there is actually natural convection because we are bound to the gravity of the Earth. The only exception is things that went into space, that's so far away that G is equal to 0. Then in those cases, there's no natural convection. So it actually means that we always have the situation where we need to take the forced convection, and we have to take also into consideration the natural convection. In general, we are going to say if there's high velocities, then the forced convection would be significant, and we would like to add to it the natural convection cases. If it is low velocity cases, then also we would like to add the natural convection. However, in most cases, if we have very high velocities, and now the question is what is high, of course, if we've got significant velocities, then normally this part is negligible in comparison with the high velocity cases. So in general, what do we use as a criteria? With the previous lecture, I've showed to you the relationship of Grashof number divided by the Reynolds number square. That is a good criteria that can be used to determine when is the flow actually all forced convection, when is it natural convection, and when should we combine the two effects. And we've said that the Grashof number divided by a Reynolds square is smaller than 0.1, then the natural convection effects are negligible. Okay, natural convection negligible. If Grashof divided by Reynolds square is typically, I can rather do it like this. If Grashof divided by Reynolds square is smaller than 1, the natural convection is negligible. If Grashof divided by Reynolds square is larger than 0.1 and smaller than 10, then neither are negligible. And if the Grashof number divided by Reynolds square is larger than 10, then forced convection is negligible. In general, and I've mentioned it already when we've discussed chapters 6 to 8, is that the Nusselt number is a function of Reynolds number, Prandtl number, and Grashof number. For all these three cases, Reynolds, Prandtl, and Grashof, and Nusselt number is a function of Reynolds, Prandtl, and Grashof. Sorry, this must be 0.1. Okay. Sorry, and this one must be 10. There you go. Okay, is that fine now? Okay, yeah. So, if Grashof divided by Reynolds square is smaller than 1, then it means natural convection is negligible. Therefore, then the Grashof number doesn't play any role. In this case, forced convection is negligible, which means that the Reynolds number doesn't play a role. And obviously, with mixed convection or combined convection, then the Nusselt number is a function of Reynolds number and Prandtl number. In your textbook, there's a sketch, typically of a vertical flat plate, of firstly, the equations that can be used for forced convection if we plot Grashof divided by Reynolds square, and if we plotted the Nusselt number, the local Nusselt numbers, divided by the local Reynolds number to the half, then the forced convection results are going to give a line like that. So it actually means that it's not a function of Grashof number. The natural convection results would give something like that. And if we go and do experiments, then we will find that typically for the experiments are shown for air, typically for a Prandtl number of 0.72, and then some lines are also shown for different Prandtl numbers. Then we will see that typically the experimental results will do something like that. Now, in these types of problems where we have combined convection, there can be three possible scenarios. And that is best illustrated with, firstly, a hot plate. So if that is a hot plate, then we know the buoyancy forces. BF is the buoyancy forces. The buoyancy forces will go up. If we would now add a fan here, the forced convection forces also going in an upward direction, then we will call this type of situation assisting flow. Thus, if you didn't add a fan, you'll get a certain heat transfer coefficient. When you put the fan on, the heat transfer coefficients will increase, so it assists. The other case is now where we've got a cold plate. Of course, gravity is in that direction. So now we've got the cold plate. And for a cold plate, the boundary layer would start there, and the buoyancy forces will now go in that direction. If we now also put a fan here, and we look at the forced convection forces, then we will call this case opposing flow. Opposing flow. Thus, if we didn't have a fan, we will have certain heat transfer coefficients because of the flow in a downward direction. But if we put the fan on, you'll immediately understand that the heat transfer coefficients are now going to be less because it is being opposed by the forced convection forces. And then the third one is the one that I've showed you the sketch previously, where normally the buoyancy forces would do something like that. Okay, and now we put the fan here. That would be the forced convection, and the resultant streams of flow will now actually move into that direction there like that. So if you just think of this situation without the fan, you will have certain heat transfer coefficients. When you put the fan on, the heat transfer coefficients will increase. So there is also, although we call it transverse flow, transverse flow. We have the flow, that the situation therefore that we can say, in this case the heat transfer is enhanced. The heat transfer coefficients will improve because of this situation. In this case, the forced convection will resist the natural convection, and in this case it will enhance. Okay. Now these three scenarios are very important, because if we now would look at the situation of determining this Nusselt number, and let's suppose this Nusselt number is 10, okay? And we've got forced convection, and we would get the Nusselt number only for forced convection, and let's suppose this Nusselt number is 20. Then many of you, or most people, would actually add the two Nusselt numbers. You'll say it is equal to 30. Okay. So let's suppose the Nusselt number for forced convection is 20, and the Nusselt number for natural convection is 10. Okay. Then the natural thing is that people will say, well, the total Nusselt number is now equal to 20 plus 10, and that is equal to 30. Okay, now that is incorrect. That is not how we determine the combined Nusselt number. The combined Nusselt number we have determined with experiments. Can be written as Nusselt to the n for forced convection plus Nusselt to the n for natural convection to the power of 1 divided by n. If we do it like that, then it works. However, if you go and look very carefully, you'll see there's a plus and a minus. Most students do not see this plus or minus until they test an exam. Then for the first time they realize, well, what is going on with this plus and minus? Why is it plus or minus? Is it now plus, or is it minus, or is it an error in the textbook? Well, the answer is it is being determined by exactly what I've mentioned here. Okay, so if the flow is being enhanced, then it should be a plus. Okay, if it is being resisted, then it should be a minus. And normally, n is in order of about 3 to 4, and from experiments it has been determined typically for vertical plates and vertical types of geometry, n is approximately equal to 3, and if it is horizontal types of plates, then normally n is approximately equal to 4. Do you understand the theory, ladies and gentlemen? Right. Now let's do an example. The example that we're going to do is that of a vertical flat plate with dimensions of 200 millimeters by 200 millimeters. The surface temperature is 40 degrees Celsius, so it's not very high. And the environment temperature is 20 degrees Celsius. And the question is, what will the heat transfer coefficient be, or the heat transfer rate be, for firstly the case where we've got a fan here with a velocity of 0.4 meters in the upward direction. In comparison with putting the fan on that side with the same velocity. So in the first case, the flow is going downward. In the other case, it is going upward. The forced convection cases. Okay, so in terms of properties, we need to get the properties at the average of the surface temperature and the environment temperature. So that is at 30 degrees Celsius. 30 degrees Celsius, we work with air. It's in table A15. You can get all the properties for air, and the properties are thermal conductivity K of 0.02588 watts per meter Kelvin, kinematic viscosity of 1.608 multiplied by 10 to the minus 5 square meters per second. The Prandtl number is equal to 0.7282, and beta is not given in the table, but it's air, so we can assume it's an ideal gas. So it is 1 divided by 273 plus the temperature at 30. So there's all the properties. Are you still writing, or are you with me? Okay. So if we now look at the theory that we've done here, then we can see we've got forced convection and natural convection. The first thing that we think of when we've got forced convection is getting the Reynolds number. And the first thing that we think of with a natural convection problem is to get the Grashof number. So those are the two things that we need to determine now. So let's determine the Reynolds number. The Reynolds number is equal to the velocity multiplied by the characteristic length divided by the viscosity. The velocity is 0.4. It doesn't matter if it's going up or down now. In both cases, the velocity is 0.4. The characteristic length is 0.2 in that direction, divided by the kinematic viscosity, which is equal to 1.608, multiplied by 10 to the minus 5. So if we calculate the Reynolds number, then it is equal to 4,975. That would tell us the flow is laminar. Remember, for a flat plate, transition occurs in the order of about 500,000. So we are far away from there. The Grashof number is equal to G beta Ts minus T infinite multiplied by L to the third divided by the kinematic viscosity squared. If we look at the PowerPoint quickly, Tamara. If we look at the PowerPoint, we see for a vertical plate that the characteristic length that we need to use is that length there, which in our case is 200 millimeters. And there's the ranges for the Rayleigh number, and there are the equations that we can use. So the Grashof number is equal to 9.81 multiplied by 1 divided by 273 plus 30 beta. The surface temperature of the plate is 40. The environment temperature is 20. And the characteristic length is 0.2 to the third divided by the kinematic viscosity 1.608 multiplied by 10 to the minus 5 square. And the result is equal to 2 multiplied by 10 to the 7. The Rayleigh number would be the Grashof number multiplied by the Prandtl number. So you can go and write down the value to determine the Rayleigh number. And then to determine which equation should be used. Okay, and that is what I also did when I select one of the equations. But before we do that, we need to determine what type of problem it is. Can we ignore the natural convection and just calculate the problem using the forced convection results? Or can we ignore the forced convection and only consider it as a natural convection problem? So this ratio is then important. That is equal to 2 multiplied by 10 to the 7 divided by the Reynolds square is equal to 4975. And that gives us a value of 0.809. 0.809. So, if we look at this, we see that this is a problem where we have to take into consideration both the Reynolds number and the Grashof number. It is a combined problem or a mixed convection problem is the other name for it. So mixed convection, or combined convection. Okay. So from that, we first need to get the forced convection results. The Rayleigh. Let's first do the natural convection. That is equal to the Nusselt number is equal to 0.59. Rayleigh to the fourth. So that's one of the equations that I've selected there based on the Rayleigh number. It's 0.59 multiplied by the Rayleigh number, 2 multiplied by 10 to the 7. Remember, that is just the Grashof number. We get the Rayleigh number by multiplying the Grashof number with the Prandtl number. The Prandtl number is 0.7282 to the fourth. And the result is a Nusselt number of 36.42. Okay, and let's write here natural convection. The Nusselt number for a natural convection problem only. Okay, so this equation is being selected based on this Rayleigh number. That is the Grashof number. The Grashof multiplied by Prandtl is the Rayleigh number. Any questions, ladies and gentlemen? Yep.
Is it 36.42 or is it 3,640?
Sorry, it's 36.42. 36.42. Okay. Now we have to go and get the forced convection. For that, you have to go back to the chapter, I think chapter 7, on external forced convection, where we did the flat plate. Now, for the flat plate, there are several equations. Again, what is important is to look at the Reynolds number. In this case, the Reynolds number is laminar. So if we go and select the equation, then the equation for forced convection is equal to 0.664 Reynolds L to the 0.5 and Prandtl to the third. And this is equation 19 in your textbook. Okay. And this equation is equation 721, chapter 7. It is equal to 0.664 multiplied by the Reynolds number. The Reynolds number is 4975 to the 0.5 multiplied by the Prandtl number is equal to 0.7282 to the third, and that will give us a Nusselt number of 42.14. 42.14. So, the Nusselt number for combined heat transfer is then equal to the Nusselt number for forced convection plus the Nusselt number for natural convection, and that is equal to 78.56. Good. So this is exactly what you shouldn't do. The right way is to say that the Nusselt number combined is equal to the Nusselt number for forced convection. And now we have to go and look at the situation. So let's do the situation where if that is the plate and there's the fan, it's going in that direction and in that direction. So what do? They oppose each other. So therefore, it should be negative. Okay. To the n minus Nusselt number of natural convection to the n, everything 1 to the n. Right, so it is equal to 42.14 to the power of 3 minus 36.42 to the third, and everything to the power of 3 and everything to the third, and that would give us a Nusselt number of 29.8. Right, now for the other case, then that is the plate, and there's the fan. The buoyancy forces go up. The force of forced convection is in the same direction, so then the Nusselt number would be forced convection to the n plus the Nusselt number natural convection to the n, everything to the minus third. So the difference between the two problems is, firstly, we're going to use the negative sign, and secondly, we're going to use a positive sign. Okay, so if you go and do the substitution there, you'll find that the Nusselt number is 49.8. So thus, if we look at the problem, there's the plate, there is the fan like that, the buoyancy forces go up, the forced convection forces go down, then the Nusselt number for the combined would be equal to 29.8. The Nusselt number is equal to the heat transfer coefficient multiplied by the characteristic length divided by K, is 29.8. We want to get the heat transfer coefficient multiplied by 0.2 divided by the thermal conductivity is 0.02588 is equal to 29.8, from which we can get that the heat transfer coefficient is equal to 3.085 watts per square meter degree Celsius. If we use it to get the heat transfer rate, the heat transfer rate is equal to the heat transfer coefficient multiplied by the surface area multiplied by Ts minus T infinite. Excuse me. The heat transfer coefficient is equal to 3.085. The surface area is 0.2 multiplied by 0.2. I didn't say that if we should look at both sides of the plate. So this is only for one side of the plate. The surface temperature is 40 minus 20. So the heat transfer rate would then be equal to 3.1 watt. And that would be per side. If we would consider both sides, then it would obviously be 6.2 watts of heat being released. Okay. So that's the one part of the problem. The other part of the problem is if that is the plate, and now we've got the fan here, the buoyancy forces go up, the forced convection forces are also going up. So the heat transfer rate combined is then equal to this higher value, which is 49.8. Okay. What do I write? It's not the Nusselt number, it's the Nusselt number. Combined Nusselt number. The Nusselt number is equal to the heat transfer coefficient multiplied by the length divided by the thermal conductivity, 0.02588. That is equal to 49.8. from which we can get that the heat transfer coefficient is now equal to 6.444 watts per square meter degree Celsius. So we can see that the heat transfer coefficient was previously 3. In this case, it is about double, 6.44. And then we can determine the heat transfer rate again as the heat transfer coefficient multiplied by the surface area multiplied by the surface temperature minus the temperature of the environment. And that is equal to the heat transfer coefficient, which is 6.44, the surface area, which is 0.2 multiplied by 0.2, 40 minus 20, and the heat transfer rate is then equal to 5.155 watts. And again, this would be per site. If we consider both sides, then it would be about 10 watts. Any questions? Yes.
What would you do if both the fans are blowing at the same time?
If both of them are blowing at the same time, yes. That's an interesting one. I suppose that the two forced convection ones would cancel each other out. In practice, however, I'm not so sure, because I think that in this case, the flow would be nicely laminar over the surface. I think if you've got two fans from opposite sides, then there will be flow separation on the plate, and most probably the heat transfer coefficient will be higher. But again, remember the equations which are given in your textbook and the table, for example, table 9.1. Those are just a selection of the most easiest cases known in literature, and it is just to make you familiar with the concepts. So if you've got something like that, then you need to go into literature and you need to get results from experiments that has been conducted from which you can get it. Okay, and the results will normally be in tables, graphs, or empirical equations. Okay. So, any other questions? Okay. You will see that in natural convection we are talking of small heat transfer rates, 3 watts, 5 watts. Okay. And this is actually one of the challenges that the people have in the computer industry. All these chips which are running at higher and higher speeds, they're releasing more and more heat. So for the past 10 years or so, the barrier in terms of making PCs, which are orders of magnitude, not only PCs and desktops and cell phones, to make them orders of magnitude faster, but also orders of magnitude cheaper. So you can think of a laptop these days, a good laptop, 10,000 Rand. How do you get it to 1,000 Rand? Well, the challenge is the cooling. The cooling is the limitation at this stage, trying to get rid of the heat. So for that reason, over the years, they've tried many solutions for it. Firstly, fins, then fins with fans, and at this stage, they are looking at condensation and evaporation on the outside so that you can get heat transfer coefficients of orders of magnitude of 10,000 and more, because then you can get all the heat out. But it means that when you start using these complicated systems, then you start using fans and pumps, and the reliability of those are issues. So it is an industry in which a lot of work is being conducted at the moment. However, the challenge still remains. You need to get 60 watts out of 1 square centimeter. Well, not only 60 watt, 100, 120 watts, and even more out of 1 square centimeter. That is the huge challenge at this stage. Right, ladies and gentlemen, if there are no more questions, then we've completed this chapter. Thank you very much.